But that's also, when I was digging online for some questions, asking people that already online with us or here, what they would like to ask you about the Interstellar. And first, we can come up with three key aspects. You can correct me on that, of course. The time dilation is one of them, and that was baked into the music of the movie. The wormhole, space traveling, and the black hole, and that's the one that most people at least need some explanation on. So let's take them one by one. In the movie, let's start by the time dilation.
Yeah, so the time dilation, of course, the movie describes the time dilation very powerfully because you see Murph, Cooper's daughter. You meet Murph when she's about 10 years old, early in the movie. And then you see her quite extensively when has become a physicist, and she's working together with the God, it's so long since I've looked at that. Anyway, so she's become a physicist and is working on trying to understand the gravitational anomalies in order as a tool for trying to understand how to save humanity. And then you see her as a very old lady at the end of the movie. And in that whole process, Cooper has only aged by an amount of a couple of years in that entire process, while she has moved from age 10 to age 95. And so something has gone crazy about time, and that is time dilation. The thing that was particularly most interesting for me on the time dilation was when Christopher Nolan said to me, I want 1 hour down on the surface of Miller's planet, the water planet in the movie, to correspond to 7 years up at high orbit and back on Earth. And I said to him immediately, that's not possible, because any planet that's as close enough to a black hole to have that much time dilation, it will surely be in an unstable orbit and will fall into the black hole and be gone. He said, Chris said to me, by then he knew me quite well, he said, okay, well, that's your initial answer, but you could well be wrong. Go do a real calculation. Don't just use your intuition. Go do the mathematical calculation. So I did. Then I discovered that he was right and I was wrong. That in fact, if the black hole is spinning fast enough, then in some sense, the centrifugal forces associated with the dragging of space into motion, the so-called frame dragging, they enable the planet to still be in a stable orbit around the black hole, close enough to the black hole that indeed 1 hour on the planet, that close to the black hole, is 7 years back on Earth. But it's a beautiful example of the true answer comes from a detailed calculation of the laws of physics, not my physical intuition, which was wrong, and or from observation. Well, you see the observation in the movie.
That's great. And so our next step will be, as I said, the wormhole. So usually we think, or people, if they saw any of the sci-fi movies, they say, okay, we're going to the wormhole. But what happens? Like, I remember one of my friends that work in the field, he tried to describe it as a tunnel in space, but no time. Can we say something like that?
Yeah, that's so the wormhole that appears in the movie Interstellar, that is basically right. There is no significant amount of time dilation in the wormhole, but it is a tunnel in space, or a tunnel through the higher dimensions, through what a physicist would call the bulk, to enable you to get from one region of our universe to another. It's a shortcut through the higher dimension. And I first, well, wormholes were first explored in general relativity by Einstein himself and Nathan Rosen, who was a young colleague of his, in 1935. they came to be called at that point an Einstein-Rosen bridge. It was John Wheeler who changed the name to wormhole, and thinking of the wormhole through an apple as being an analogy for to get by a shorter route from one side of an apple to another. Um, but the mathematics of wormholes uh, was pretty clear already to Einstein and Rosen in 1935. But what they did not know, and Wheeler and his collaborators discovered, was that wormholes are unstable in the sense that a wormhole will pinch off very quickly if you don't do something special to prevent it from pinching off. It'll pinch off before you can travel through, even if you're traveling through at the speed of light. And so when Carl Sagan said he wanted to go through a black hole in the movie Contact to get to the star Vega, I said, no, you have to, let's use a wormhole, but you have to have a way to hold the wormhole open, or else it will implode. And that's when I, together with my students, began work on the issue of holding wormholes open. And that's been a major research effort among experts in relativity for several decades. We know that to hold a wormhole open, you have to thread it, put into its interior something that repels gravitationally, basically holds the wormhole open through a gravitational repulsion. And we know that you can make such stuff that repels gravitationally. It is something that has negative energy. And you can get negative energy by modifying vacuum fluctuations. So the key is vacuum fluctuations, which occur in quantum theory. If you take a box, remove everything you possibly can remove, the stuff that's left is fluctuations of virtual particles, virtual protons and electrons, fluctuating in and out of existence inside of it. And those vacuum fluctuations, if you modify them appropriately, you can wind up with one region of space that has reduced vacuum fluctuations, repels gravitationally. Another region that has increased fluctuations, it attracts gravitationally. And so the whole theory of vacuum fluctuations becomes a foundation for really understanding holding wormholes open and many other topics in the universe. And so that's the bottom line of all the research that's been done on this, I think, is that it's quite likely that you cannot put enough reduced vacuum fluctuations inside a wormhole to hold it open. But we still don't know that for sure. And it still is an open question.
That's a very interesting to hear about it because, as you said, as long as I heard about wormhole, I know it's unstable and it's going to be collapsing. People can imagine it as a vacuum tube, sort of, that will squash, and then you need to find a way to make it still open, and this where the idea of the quantum fluctuations comes into the game. And I wonder if you will be writing a book about that. Saying the wormhole is an interesting topic itself.
I actually have. So I have this book of my poetry and paintings by Leah Halloran, a great painter, that came out about a year ago. That it covers many aspects of warp space-time, but not vacuum fluctuations. We have an addendum on vacuum fluctuations that we've been working on that I'm enthusiastic about, but it's not ready for prime time yet. And we don't know in what form we're going to put it out, but vacuum fluctuations are an absolutely beautiful subject
Yes.
in physics, and in cosmology and in modern technology. They are the foundation for quantum technology, for modern quantum technology.
And yeah, for our audience, this is the book Kip are referring to, if I understand it correctly. It's going to be hard, but it's a warping side of our universe. It's this book over here. It's a new book. I encourage everyone to read it. Have been enjoying looking to it the last couple of weeks. The orbit side of our universe, and you will find a very interesting pictures about it inside, how the spinning black holes are working, and many other very nice artistic work too. So I encourage everyone.
Let me just say of this book was really an experiment to try to see if we could develop a new way of communicating science to non-scientists. And this way is this mixture of verse and paintings, tightly integrated, tightly coupled. And I think my conclusion from it and from people's reaction to it is that it really is a powerful way to convey the basic ideas behind a topic in science, such as warped space-time. But if you want to go into detail, it's not as good as more ordinary kinds of science communication. But to get an initial introduction to a topic like black holes and wormholes and gravitational waves for people who are very far from it, it's a very powerful way to give this initial introduction.
I fully agree. Especially you add I wouldn't say the picture, but you add the vision over there. You can see in the background of the blast the artistic work of how an artist can picture your words. So I can see it as two people try to bring the two worlds together, the art world and the science world together. And also, since we are at the topic, I would like to remind everyone that there are a book already outside, The Science of Interstellar. That can be visible over here. So the science of Interstellar is related to the movie Interstellar, explaining the physics of Interstellar into details. So if anyone likes the movie, want to know more about it, that's the book. Find it again online through Amazon or anything else. So that's very interesting. So my last question related to this part, Kev, was related to the black hole. What's happening in the vicinity of black hole? I know that we have the event horizon, and then out of that, do we understand what's happening after the event horizon? Everything happened in the movie was before that part.
Yeah. So, well, no, in the movie, Cooper does go inside the event horizon. You see him go inside. You see him turn around, and the camera turns around, looks out from inside the black hole, and you see the universe above in a narrow circle above, which is how things are, because basically everything involving the black holes and the wormholes that you see in the movie is based on computer simulations that were done solving the equations for the propagation of light through and around wormholes and black holes. But anyway, the black hole then in Interstellar, however, is an accurate representation of what it would really look like if the black hole is surrounded by a thin disk of hot gas. That's not the way that black holes normally occur in the well, let me start over again. Since the movie Interstellar came out, the Event Horizon Telescope has made images of black holes, observational images. They look somewhat similar, but not exactly the same, because the gas is moving in 3 dimensions. It's not in a thin disk or in the equator. And so I'm very eager to see movies in that from the Event Horizon Telescope, which will show us then the flow of the hot gas around the black hole and how magnetic fields influence that flow. It'll be really, really wonderful coming out sometime in the next few years. But the physics of the black holes in the movie is really not very rich compared to the physics of black holes that we have in LIGO. when black holes collide. In the movies, you do see, and you have a little bit of discussion of the fact that there are 3 singularities in the interior. That's a prediction. Of course, we don't have observational data, though Cooper did get some observational data when he went in, and
Yes, for the first time.
he came back not by going out through the horizon, but going up into the 5th dimension and coming back through the bulk. So all the stuff that you see about black holes in the movie is really as accurate as it can be based on what our current knowledge of black holes. But when black holes collide, there's an enormous greater richness that you just never see in Interstellar. The black holes have sticking out of themselves 2 vortices of twisting space. When black holes collide and merge, you wind up with 4 vortices sticking out of the black holes. Black holes don't like to have 4 vortices. And so 2 of them have to get ejected. And the whole dynamics of what goes on with these vortices of twisting space when black holes collide is really very interesting. We have learned about these things from computer simulations that were done at the same time as I was writing this book on the warp side of the universe, and the same time as LIGO was gearing up on the verge of making its observations, and at the same time as Interstellar was being filmed. And so we have today a understanding of a richness of behavior of black holes that in fact is discussed in my book with Leah Halloran, the Paintings and Verse book, that's not in other books about black holes because it's too new. But it's an understanding that is in that book because most of this understanding came from computer simulations, solving Einstein's equations on computers by a research group that I helped to start that is a collaboration largely between Caltech and Cornell universities, but also computer simulations by other groups around the world. And it's all very new and all very wonderful. And you will start seeing this in other non-technical books. The first non-technical book that really describes that is my Warp Side of the Universe book.
That's another point to emphasize at. I would like to encourage everybody to take a look at the book, The Warping Side of Our Universe. I did like the pictures, I like the simple explanation. You really will see a different perspective of the black holes spinning and everything you can imagine. And as Kev said, it's the most recent one. And Kev, we have been diving with you through your journey, how it starts, how you become a physicist, and also to the physics of the gravitational waves and the physics of the movie Interstellar. And